Hi, this is Vigyan Singhal from Oski Technology, and I want to talk to you about how you can formally verify and reuse highly configurable IP designs. We're designing a lot of systems on chips today, SoCs. A lot of these have embedded processors in them, different kinds of ARM processors, big little architectures, maybe with an interconnect or not, supporting different peripherals like a wireless data path here, DMA controllers, memory controllers, camera interfaces, low speed interfaces like I2C and so on. All sorts of IPs, security processors, video coprocessor for example. And we want to verify these designs. The problem is that we don't have the luxury to build all of these pieces from scratch each time, simply because we have these tight schedules in the consumer market. So the best thing to do is reuse IPs either from third parties or from our internal groups or from our previous chips. And as we reuse these IPs, we still want to make sure that all of these IPs work correctly. All the bugs in the chips are still our own. We are responsible for them, even though we may have used IPs from third parties. So it's important to verify everything as much as we can. The designs are very configurable. The IPs themselves are very configurable. So let's look at from the perspective of the IP provider. They're designing these IPs. They have designed them to be very extremely highly configurable because they have to support a large set of different customers with different requirements. They have to support different use models. They have to support different performance requirements. And they have so many different configurations that they are using a lot of configuration inputs to allow the designs to do different things depending on the configuration inputs or different configuration parameters. Doesn't really matter whether you use them as inputs or parameters. The problem is that these configuration inputs multiply together with each other and give rise to billions of different configurations. Suppose I'm designing this memory controller, for example. I have to support different configurations. For example, I'm going to have different memory spaces I'm going to support, all the way from 16 megabyte to 32 gigabyte, 12 different configurations. I may support different channel widths, times 4, times 8, times 16, times 32, 4 different choices. I may support different number of memory ranks, 1, 2, 4, let's say 3 different choices. Different page management policies, supports I have 3 different choices there. Different address mapping schemes, let's say I have 4 different choices for different address mapping schemes I'm supporting. Number of ports on the application side, I may be supporting 1 port, 2 ports, 4 ports, 8 ports, 16 ports, 6 possible different choices. The data widths could vary all the way from 32-bit to 64-bit, 128-bit, maybe even 300, maybe even 256 bits. So 4 different choices. If I multiply all of these configurations so far, they're already 20,000. And I have so many other different configuration choices that I haven't listed here. And then for memory controllers, for example, I have all of these DDR timing parameters like cache latencies, RAS to cache delay, the rope recharge time, and there are tens of these. So if I multiply all of these different configurations, I have billions of these different configurations. Verifying one single configuration of this is challenging enough because I have to try all possible input combinations, different timings of those, shmoo all possible different inputs. It's challenging enough. Imagine the amount of time the IP provider has spent on verifying your specific configurations, the specific configuration you're going to use in your system on chip. It's going to be a very small fraction of the total time they've spent on verification. And maybe they have never had even a chance to verify that specific configuration that you use. So if you rely on simulation to verify IPs, you have such a small chance to verify the specific IP configuration you're going to use. And that's the beauty of formal verification, is that in one single formal verification run, you can try all of these different configurations together by making them as symbolic constants. You can take each one of these configurations, apply make each one of them symbolic constants, use constraints like this here, and in one single run, the formal tool is able to verify all of these configurations for all the checkers you want to verify, and you'll be guaranteed that the IP that you're going to use has been verified for the specific configuration. What you want to do is you want to ask the IP vendor for not just the IP, design IP that's been configured for the configuration that you choose, but also the formal test bench, the checkers, the constraints, and the scripts. They have probably used all of these in a configurable style, so that before delivering the test bench, they can configure for your requirements for the configuration that you chose. And once you get the configured test bench with the scripts, you can replay and reassure yourself that the IP was indeed verified for your specific configuration and your confidence in that. Moreover, the properties that you get in this configured test bench, they are used to verify the IP vendor's design IP, but you can also use the same properties to verify your own IP, the customer IP that's integrating with the vendor IP and working together, because you want to be sure that the all possible corner cases that were verified and designed in the vendor IP have been verified with your own customer IP, and together they work seamlessly and you have no corner cases to worry about. So verifying IP, especially configurable IP, becomes extremely valuable if you do it with formal verification, and you get a level of coverage that's almost impossible to get with simulation only. Thank you so much.